What does your brand new laptop really have in common with a computer from 40 years ago? I mean, on the surface, absolutely nothing, right? One's a powerhouse, the other is a museum piece. But what if I told you they share a fundamental secret? A tiny piece of technological DNA that has powered every single processor for, like, the last half-century. Okay, let's dive in and uncover this hidden engine of the digital world.
So let's just put this into perspective. On one side, you've got the old 6502 chip from an Apple IIe. It was built from about 4,500 transistors, and it was chugging along at a few 100,000 calculations a second. On the other side, a modern M1 chip with 16 billion transistors, capable of 3 trillion calculations every single second. The difference is just, it's absolutely staggering. It's like comparing a bicycle to a spaceship.
So, here's the big question, right? How can two pieces of tech, separated by decades in this just mind-boggling gap in power, operate on the exact same fundamental principle? What is this shared DNA? Well, the answer is simpler, and frankly, it's way more elegant than you might think.
To really get our heads around this, we're not going to start with circuits and code. Nope. Instead, we're going to use an analogy. Let's imagine the entire computer is this massive library, and we're about to see how it works from the inside out.
Okay, so check this out. It actually maps perfectly. Think of the huge bookshelves way in the back. That's your long-term storage, your SSD. The cart that's zipping books back and forth, that's your main working memory, or DRAM. And the table where all the action happens, that's your CPU. On the table, you've got a calculator. That's the arithmetic logic unit, or ALU, doing all the math. There's a sheet of paper, a little scratch pad for the numbers you're working on right now. Those are your registers. And running the whole show is our library robot, the control unit. All right, so our library is all set up. Let's put our little robot to work. We're going to give it a simple program to run, which is really just a list of instructions written down in one of the books.
Now, in these books, you've basically got two kinds of pages. You've got your instruction pages. Think of this like a recipe, a numbered list of steps to follow, like load this or add that. And then you've got your data pages. Those are your ingredients, the actual numbers and values that the instructions are going to work with. You absolutely need both to get anything done. So, the job we're going to give our robot, it's one of the most common things you see in all of programming. Take a variable, we'll just call it I, and add 1 to it. It sounds so simple, right? But watching how the computer actually does this, well, that reveals everything.
And here's the key. This simple little action is broken down into 3 separate steps. First up, the load instruction. The robot goes and finds the current value of I in a data book and copies it onto its sheet of paper. Second, increment. It takes that number over to the calculator and adds 1 to it. And finally, store. It takes that new result from the calculator and writes it back into the data book right over the old value of I. That's it. That's the whole process.
Okay, but wait, how does the robot know which instruction to do next? Well, it's got this special little tracker on its paper called the program counter. After it finishes instruction number 1, the program counter just automatically ticks up to 2, telling it exactly what to do next. It's like the conductor that keeps this whole orchestra playing in perfect rhythm. All right, so we just watched our little robot do its thing. And buried inside that simple sequence of load, increment, and store is the universal secret we've been hunting for this whole time. The technological DNA of every processor can be boiled down to just 3 core steps. And there you have it. Fetch, decode, execute. This 3-step cycle is the fundamental process that the ancient 6502 and the futuristic M1 chip both share. This is the heartbeat of every single computer you have ever used. Let's break it down real quick. Step 1 is fetch. This is our robot looking at its program counter, going to that instruction number in the book, and grabbing the command. It's basically asking, all right, what's next on my to-do list? So once it's fetched the instruction, it's got to figure out what it means. That's step 2, decode. The robot's internal brain, its circuitry, looks at the command and goes, okay, load means I need to go get a value from a data book. It's that moment of understanding. And you guessed it, the final step is execute. This is the get-it-done part. The robot actually performs the action. It sends the signals to the calculator to add, or it picks up its pencil to write a value back into the book. The command is finally carried out. And here's the mind-blowing part. The processor doesn't just do this once. It's in a constant loop, repeating this fetch, decode, execute cycle over and over and over again. On an old computer, this happened 1,000,000 times a second.
On a new one, it's happening billions of times a second. So now we can finally circle back to our big question from the beginning. If both the old chip and the new chip are running the same basic cycle, where in the world does that 10 billion-fold power difference come from? And the answer is just so cool. The difference isn't the DNA itself, it's the evolution built around it. Modern processors don't have some new secret cycle, they just perform the exact same fetch, decode, execute cycle with unimaginable speed and at a massive scale.
I mean, just look at these numbers. The old 6052's clock ticked 1 million times a second. That's 1 megahertz. The M1's clock? It ticks over 3 billion times a second. That means every single step of that cycle, fetch, decode, execute, happens thousands of times faster. That's the speed part of the equation, right there.
And for the scale part? Well, modern chips have these incredible superpowers. Pipelining is like an assembly line for instructions, where it starts decoding the next command while the current one is still executing. Multiple cores? That's like having several of our library robots working in parallel on the same chip. And 64-bit architecture just means our robot can carry much, much bigger numbers on its sheet of paper with every single trip. So at the end of the day, the next time you're editing a video or playing a photorealistic game, just remember what's really going on under the hood. It's not some unknowable magic. It's just a ridiculously simple 3-step process. Fetch, decode, execute. Repeated with a speed and scale that is, quite frankly, awe-inspiring. A universe of complexity, all built on the very same secret DNA.